Hi, this is Professor Fernandez. This is video 3 in lesson 12. So we're still talking about related rates here. We've been doing that in these previous two videos in lesson 12. What's different about this particular example is that it's probably the hardest of the three. The reason is that, as you can see from the prompt, we're not given any information about the equation that we need to use to later relate the rates, but at least we are given a diagram. So I've actually put this in here from the textbook. So, we've done, this is video 3 now in this series. We've done two ones before, so I encourage you to check out videos 12.1, 12.2, where I review related rates. And also I talk about this box 4.1, which is sort of a guide for how you might want to set up related rates problems that, in my experience, works in your favor. So let's go ahead and read through the example. It says a traffic camera is tracking a car as it approaches in an intersection. See the figure. So let's see the figure. There we go. So that's the camera. There's the car. Assuming the camera is 300 feet away from point A. So that's the first piece of information that we should add to our diagram. This distance is 300 feet, the camera away from point A. How fast, so that's the related rates tip-off there, is the distance between the car and the camera? Okay, so this is the distance between the car and the camera. In the textbook, I call that z, so I'm going to be consistent here. Let's just call that z. You can choose any variable letter you want. So how fast is that distance changing at the instant the car is 400 feet from point A? So, it's up to you how you put in that information into the diagram, right? I'm not actually going to add it here, because if I put this down and I say this is 400 feet, many people would be tempted to just use the Pythagorean theorem and solve for z and call it a day, right? But that's not what's really happening, because that would be treating this diagram as a static picture. That would be true if this car is parked 400 feet away from point A. Then you could use the Pythagorean theorem to find z, right? But whether you pay attention to these three little lines or the fact that the problem tells you that distance is changing, this is telling you that this is really meant to be seen as a dynamic diagram, not a static one. So I'm not going to put in the 400 in the diagram. Instead, what I'm going to do is I'm going to say, okay, the question we want answered is how fast is the distance between the car and the camera? We call that z. How fast is z changing with respect to time at the instant the car is 400 feet away? So 400 feet away. Now we realize that we need something, some variable to measure how far the car is from point A. So we're going to introduce another letter here. So in the book I call that letter y, so we'll be consistent here. Let's call this distance y. So how fast is the z distance changing when y equals 400 feet? Okay, so this is where I want to put the 400 feet. In a related rates problem, most of the time, rarely ever is it not the case. Most of the time you have some when statement. You want to find a rate when some other variable is equal to some value. Okay, and then there's more information toward the end here, and traveling at a speed of 60 feet per second. So that is given information, right? So given. Traveling at a speed of 60 feet per second. Okay, let's go back to the diagram. It looks like the car is moving in that direction. Okay, so that tells us that the y, which is the distance the car travels, is decreasing, right? If you're moving in this direction, your distance to point A is decreasing. So y is a distance. The derivative with respect to time is a speed. And there is a 60 here. They're telling us the speed is 60 feet per second. But the whole point of telling you about the decreasing nature of y gets smaller as the car approaches point A, is to indicate to you that we need a negative sign here. Okay, so this is one of the things that I say in this box, but also just thinking about what derivatives represent, instantaneous rate of change, right? So y is the distance to point A on the diagram, so that distance is getting smaller because the car is approaching point A. So this speed is 60 feet per second, that's true, but in terms of how the distance changes, right, we need a negative sign because that will make the distance decrease over time. Okay, so enough of all the setting up. We have all the information that we need, except for the equation we have to use. But because we've mathematized it using more or less the procedure I advocate down here, that means that we now know the equation we need. We need an equation that relates z and y. So if we go to our diagram, we can now see that once again this turns into a geometry problem. So I have a right triangle here, and z is the hypotenuse, y is one of the side lengths, and we have 300 as the other. So Pythagorean theorem. So I'm going to say z squared equals 300 squared plus y squared. And I could square out the 300, why not? Let's do that. So that's 9,000 plus y squared. And then I want to solve for dz dt. So why don't I just solve for z here? Take the square root of both sides. I don't want to do a plus or minus, right? Because if I look at the minus part, then z is a negative distance. That doesn't make sense with the diagram. So I don't want to take the negative root here when I take the square root. So this is the equation that I'm going to use. This is the equation that relates z and y. And now what I have to do is find the derivative of z with respect to t. We've talked a few times now about whether you use the Leibniz version of the chain rule to do this, or sort of the version of the chain rule that is uses like y of t and z of t. I'd like to use the Leibniz version. It's a little cleaner. So I'll do that here. So I'll say dz dt is dz dy, right? The actual variable that shows up here, times dy dt. So this tells us that we're going to have to find the derivative of z with respect to y down here. And then whatever that is, we multiply it by dz dt. Great, so I will give myself some more room by erasing things here, right? I'll keep that in memory so that we use them when we come to the end of the problem. So dz dy, what is the differentiation rule that we're going to use? Well, so z is the square root of 9,000 plus y squared. Y squared is therefore sandwiched under the square root, so we're going to need a chain rule. So z is 9,000 plus y squared raised to the 1/2. So the derivative of z with respect to y, dz dy, we would bring down this 1/2, subtract 1, giving us negative 1/2, evaluate it at the inside, and then multiply by the derivative of the inside with respect to y. Derivative of 9,000 is 0, derivative of y squared, power function, power rule, so 2y. So that's dz dy. So therefore, that's what these three dots means. Dz dt, we said by the Leibniz rule, was dz dy, dy dt. So we take this function we just found, let's just cancel out the 2's for now, and bring the 1/2 downstairs. So we get y over the square root of 9,000 plus y squared. That's dz dy times dy dt. So this is the equation that finally relates the rates, right? That's the related rates problem. And now we go back and we just put in all the information that we have. So we were asked to find dz dt when y was equal to 400. So I'm going to put 400 over there. Also going to put a 400 down here, 400. And then also remember we had said dy dt was negative 60, negative again because the distance y was decreasing. So put negative 60 here. Okay, so at this point we churn all this out. You can use a calculator, you can simplify, and we end up getting negative 48. Let's talk about the units, the last thing to do. So Leibniz form of the derivative is very useful for that. You see that z was a distance, if we go back to our diagram, between the camera and the car. Sorry. We had measured distances here in the entire problem in feet. So z is in the numerator, so that should give us a unit of feet. The denominator t we've been measuring as time in terms of seconds, right? Speed was 60 feet per second. So t here is in the denominator, so the unit of seconds goes in the denominator on the right-hand side. So that's it. This is the numerical value for dz dt. The last thing that I will mention here is about it being negative. So this is what I would call, just a check on your work. If we go back to the diagram, right, let's just remove all the math and let's just think about this happening in the real world, right? So you have this car that is traveling in this direction and the camera is tracking the car. We have just found out that what we called z, that distance, is changing at this rate. The rate is negative, right? Which tells us that the distance should be decreasing. And the answer, the question is, does that make sense? as this car travels up, does it make sense that this distance would be decreasing? And it should make sense to you, because as the car travels up, right, you take it to the limit, if you will, when the car actually reaches point A, we know that it was going to be 300 feet away from point A. We were given that information in the problem, right? But where the car is right now as pictured, it's 300 feet. The camera is 300 feet from point A, and the car is Y feet from point A. And the Pythagorean theorem tells us that Z, therefore, is equal to this, right? The square of 300 plus Y squared, square root of that. So, it makes sense, it should make sense at least, that as the car is traveling that way, this Z distance is decreasing, right? If the car were traveling in the opposite direction, right, then you can see me here drawing longer lines, right? Then Z would be increasing when the car traveling in this direction. But Z here is decreasing. I'm drawing shorter and shorter and shorter lines until I get to 300 when the car gets to point A. Okay, so again, this negative sign makes sense as a reflection of that decreasing measure of distance for Z.